Hi students, today is the second session on the second law of thermodynamics, my dear students. And in today's session what we are going to do is basically working of the heat engine, working of heat refrigerator, alright, or heat pump that we call it as, and the efficiency of the Carnots engine. Alright students, so this is going to be the agenda of this particular session out here for today. Besides that, we are going to look at a few numericals based on these concepts, and those numericals are going to be first, the type of numericals that we are going to look at. First, we are going to look at some basic questions on the working of the formula, the formula of the efficiency formula, okay, of the heat engine. Second, we are going to look at the efficiency of any cyclic process, not Carnot's one, but any cyclic process, how to find out the efficiency of a given cycle, okay, of cyclic process. The third one we are going to look at is there's a heat engine. Now, if it is worked in a reverse direction, okay, so that will be working as a refrigerator, right? So how to have the relations between the efficiency and the coefficient of performance of the heat engine and the refrigerator. So that's the third thing. And the fourth numerical will be based on the Carnot cycle. All right. Fine students, so this is like the agenda for today's session. Let's go ahead to the first concept itself, that is the working of a heat engine. So what do we have here? In the working of a heat engine, we looked at something like, there is a hot reservoir, alright, that is like, the fuel is burning at that place, so temperature is kind of very high out there, okay, say this is at temperature T1 or TH. Now, the engine kind of takes in heat from that particular section, okay, so there is a piston out here, alright students, so it takes heat and it does some useful work, that comes out, so our car kind of moves, right? And some amount of heat it kind of throws out to the atmosphere. Alright, so this is basically the working of the heat engine out here. Now, what are the formulas which are associated in this particular section? Students, we can clearly look at here. The work done is going to be based on the conservation of energy. It extracted QH amount of heat. It liberated QC amount of heat. So total work is going to be QH minus QC. Alright, so this is the heat coming from the hot reservoir. This is the heat going to the cold reservoir out there. Alright, now next, we get the work done. What is the efficiency of the engine? Efficiency of the engine is nothing but equals to work done divided by the amount of heat it actually absorbed. Work done divided by the amount of heat actually observed. So W amount of work किया इसने, कितना heat accept किया था उसने, QH. Now as per this, my W is equal to what? QH minus QC divided by QH. Alright students, divide कर दो यार, you get this as the standard formula. Alright students. Acha, another thing. Now I'm going to bring it right here itself because of the very fact, in the last entropy section, my dear students, we said that the maximum efficiency could be there for delta S equal to 0. And when delta S was equals to 0, I told you that this relation holds valid, that is my QC by QH is equals to TC by TH. Where did it come from? We had calculated entropy of an engine and we equated it to 0 for max efficiency, my dear students. Alright, this is also something that we are going to look at in the working of a Carnot's engine. Carnot's engine also exactly we are going to derive the same thing. Alright, however, it comes from the basic concept or the fundamental concept of the change in entropy. Maximum efficiency will come when the change in entropy is equal to 0, for which we get QC by QH is equals to TC by TH. Anybody wants to refer it, go back to the last video, have a look at it, you will understand the concept out there. Fine students, let's go ahead directly to questions right now. Okay, so the first question, so what I have done is I have taken some basic questions initially. So let us work on those basic formula based questions, that is this particular formula that we have here. Okay, now right away, students, I have taken the Carnot's engine. Alright, let me just tell you that Carnot's engine is going to be working at the maximum efficiency, and at the maximum efficiency I know what is going to be the, so देखो अभी हम लोग efficiency वाला जो derivation है Carnot cycle में क्या क्या different processes है, we are not going to do that. We are going to do that towards the end in today's session only, but right now for this purpose of the numerical, we know efficiency is equals to 1 minus Q cold by Q hot. All right. This can also be written as 1 minus Tc by Th. So we kind of looked at it from the previous slide. Previous slide में हमने यही idea देखा था. अच्छा, अब देखो, we need to find out the efficiency. We will find it out later down the line, but that is the next question which we have. Here in this question, let us look at it from this. साफ साफ देख रहा है. From the hot reservoir, it is accepting 6 into 10 to the power 5. My dear students, there's got to be a slight error out here. This is calories. Okay, 6 into 10 to the power 5 calories it extracts from the hot. This is at 227 degrees centigrade. The cold is at 127 degrees centigrade. Then they are asking us, my dear students, what is going to be the value of Q2? That means how much heat, कितना heat ये cold reservoir को छोड़ देगा. ठीक है. अच्छा, for this, my dear students, the simple idea तो क्या ही है. For maximum efficiency हमने क्या देखा था? QC by QH is equals to TC by TH. All right, which implies your QC जो कि पूछा गया है इस क्वेश्चन में, that is your Q2 will be equals to QH into TC. TC कितना है? Temperature of the cold. This is 400 Kelvin. This is 500 Kelvin. So this will be equals to nothing but 400 divided by 500, my dear students. This goes out. We are going to be left out with how much? 6 into 4 divided by 5 into 10 to the power 5. So this is going to be 24 divided by 5, which will be equal to 4.8 into 10 to the power 5 calories. All right. Simple equation में based किया हुआ question, my dear students. All right, I hope everybody got it. Let's move ahead to the next question. In the next question, they have asked us what is the efficiency. तो चलो, all the aspects of this formula, let us explore it and get it done. So they have asked us what should be the efficiency of this particular heat engine that we kind of see here. Simple idea. Okay, we can directly calculate it from efficiency is equals to 1 minus Tc by Th. So this is going to be 1 minus 400 divided by 500. So this is going to be like, efficiency in terms of percentage अगर हमने पूछा है, so this entire thing is going to be multiplied by 100. So you multiply this by 100, my dear students. How much is it going to be? This is going to be 0.8. 1 minus 0.8 is 0.2 into 100. This is going to be 20%, my dear students. So this is option A is the correct answer. All right, basic formula. Let us go ahead to the next question, my dear students. What do we have in the next question? In the next question, they are asking us what should be the temperature of the source to increase the efficiency to 30%. Again, not a very difficult one. So let us say the efficiency is now become like your 30%. So let me take it as 0.3. This should be equals to 1 minus Tc by Th. Tc is not going to change. Tc is going to remain at 400 divided by Th. This is the new one, or I'll call it as dash. Then as per the formula क्या हो जाएगा दोस्तों? 400 divided by Th dash is going to be 0.7, which implies your Th dash will be equals to 400 divided by 0.7. So this will be approximately equals to 571.42, my dear students. Okay, so this is in Kelvin. And if you have to convert it into degree centigrade, minus 273, this should be equals to option D, my dear students. So based on this, बहुत ही simple, आपके board level का question नहीं है, ठीक है? But again, concepts are concepts. Once you learn it, it will definitely help you at some point of time or the other. All right, chalo guys, let's go ahead and let us look at the next concept, which is kind of very interesting and useful for us. What do we have here? All right, now let us look at the working of a refrigerator, my dear students. अब refrigerator आपका क्या करता है? हीट इंजन तो हॉट रिजर्वॉयर से हीट एक्सट्रैक्ट करेगा, सम वर्क इट इज गोइंग टू डू टू मूव द पिस्टन एंड द रेस्ट ऑफ द हीट इट इज गोइंग थ्रू to the external surrounding, all right, or to a cold reservoir. Now here in this refrigerator, the work of the refrigerator is to extract heat from a region of a cold region at a temperature which is very low out there. And who does that work? The compressor is actually doing this particular work. It is able to extract it from this particular region and throw it out into the atmosphere, my dear students. All right, now how do we actually look at the working function of this? Now this is exactly opposite to what generally happens as a case of spontaneity. Heat is going to flow from a region of higher temperature to a region of lower temperature, and वो बदले में कुछ काम भी दे देगा, ठीक है? But out here, my dear students, the heat is flowing from a region of a colder temperature to a region of higher temperature. So some external work has to be done, and that is done by the compressor, my dear students. अच्छा, this is exactly the same. Waterfall, जैसे पानी ऊपर से नीचे आ रहा है, अपने आप पानी नीचे से ऊपर तो जा नहीं सकता. You need to have some electrical pump in order to do that particular thing. Same is the case out here. Heat can naturally, it does not flow from a region of lower temperature to higher temperature. So we need a compressor to do that particular work, and the compressor is doing that work to extract the heat from this zone and throw it out into the atmosphere so that this region can remain cool completely. All right. So this is the working principle. It is extracting Q1 amount of heat, work done W, Q2 goes out. All right, students. Fine. Now what is the working formula? हम measure कैसे करते हैं? Like like we had the efficiency of the heat engine. That means engine से हमें क्या चाहिए था? How much amount of work it will be able to do. So work was in the numerator, and how much we have given to it. So we have given it the amount of heat that was QH. All right. Now here in this case, what is the coefficient of performance for the refrigerator? So for the refrigerator, what is the function of it? It is able to extract heat. So it is extracting Q1 heat. More is the amount of heat it is able to extract, better is its performance. All right. And for that, how much work did we do? The work done is coming in the denominator. That means जितना कम काम करके हम ज्यादा heat extract कर पाए, that is the better is the performance or the coefficient of performance of the refrigerator. All right. So W, my dear students, is nothing but equals to Q2 minus Q1 from the conservation of energy. So this is the working formula of my refrigerator. All right. Now here, my dear students, the most important thing or the questions जो refrigerator related आता है, डायरेक्टली तो ये फॉर्मूले बेस पे नहीं आता. नाउ दे जनरली हैव दिस पर्टिकुलर कंसेप्ट हियर. लेट मी जस्ट टेल इट टू यू. वर्किंग ऑफ द हीट इंजन एज रेफ्रिजरेटर, ये बोलेंगे कि देयर इज अ हीट इंजन एंड इट हैज टू वर्क इन अ रिवर्स वे टू ऑपरेट एज अ रेफ्रिजरेटर. देन इफ द एफिशिएंसी इज गिवन टू यू, देन व्हाट विल बी द कोएफिशिएंट ऑफ परफॉर्मेंस? सो नेचुरल वर्किंग ऑफ द हीट इंजन में क्या होता है? देयर इज hot reservoir, we are extracting Q1 amount of heat. It is giving us, this blue line is heat engine. All right, the red line is refrigerator. Just observe it. It is exactly the reverse. Hot reservoir, work done, this. Refrigerator, cold region se heat is coming, W amount of work is happening. It is going out to the atmosphere. So it's just the inverse of it, my dear students. Let us try to find out a relation between the coefficient of performance of the refrigerator and the efficiency of the heat engine. It is going to help us in a lot of numericals ahead of us, my dear students. Okay, so let us see this. What did we see? Beta, coefficient of performance, is equal to the amount of heat extracted, say from the cold region, easier to understand, right, divided by the amount of work done. Clear? Efficiency equals to the amount of work extracted divided by QH, the amount of heat it accepted. My dear students, if I take coefficient of performance into eta, what will it be? QC by QH, right, my dear students? And from the formula of eta is equals to 1 minus QC by QH, all right, what do we have here? QC by QH can be written as 1 minus eta. All right, students, that means beta into eta can be written as 1 minus the coefficient of the efficiency. So beta can be written as 1 minus the efficiency divided by the efficiency. My dear students, this is a very important formula for the working of the heat engine as a refrigerator. If you remember this formula, आपके questions बहुत आसानी से बन जाएंगे. ठीक है? So remember this. Beta is equals to 1 minus efficiency divided by the efficiency. Very cool. Okay. Chalo, let's go ahead to a question which is based on this particular concept. All right, students. So what do we have here? We have here our next question. This says there is a Carnot's engine and it has got an efficiency of 1 divided by 10 and it is used as a refrigerator. If the work done on the system is 10 joules, then the amount of energy absorbed from the reservoir. तो वही बता रहे हैं, there is a heat engine, it is being used as a refrigerator. ठीक है? उसकी efficiency दे रखी है. So what will be its coefficient of performance? We have just looked at in the last section out here. All right, students. So we have seen that the coefficient of performance will be equals to 1 minus eta divided by eta. So this is equals to how much? The efficiency 0.1. So 1 minus 0.1 divided by 0.1 will be equals to 9. Coefficient of performance. As such, coefficient of performance is equals to what? It is equals to the amount of heat extracted which is being asked to us, the amount of energy absorbed from the reservoir divided by the amount of work done, which is 10 joules. Then my dear students, the amount of heat extracted will be equals to 90 joules. This is my answer. Option B is the correct answer out here. Alright students, I hope everybody gets that. Let's move ahead to our next question. And what is our next question based on? Efficiency of a cycle. Very interesting and very important. Multiple times it has come in the JEE in the past years. Alright students, so here we are looking at the efficiency of any general cyclic process. Alright, now there are two important things that is to be remembered. Now the first thing, इसमें मैं डायरेक्टली बता देता हूं, इसमें ये जो साइक्लिक प्रोसेस है इसका एफिशिएंसी पूछा है. ठीक है, अब देखते हैं कैसे निकालना है इसका एफिशिएंसी. ओके, सो एफिशिएंसी माय डियर स्टूडेंट्स इज नथिंग बट इक्वल्स टू वर्क डन डिवाइडेड बाय द अमाउंट ऑफ हीट प्रोवाइडेड. नाउ इन द साइकिल आउट हियर, अंडरस्टैंड, वर्क डन इज नथिंग बट द एरिया ऑफ दिस पोर्शन. सो वर्क डन विल बी इक्वल्स टू पी नॉट वी नॉट. दिस इज पी नॉट, दिस इज वी नॉट. अपना काम बन गया. Divided by the amount of heat extracted from the hot region. Let us assume that. Now in this cycle, my dear students, the heat is extracted from A to B and B to C. Because try and understand, A to B is what? A to B is basically a isochoric process. Isochoric process, work done is equals to 0. Heat will be equals to nothing but the internal energy change. ठीक है. Now as it goes from A to B, volume is constant, temperature is directly proportional to pressure. Pressure is increasing, temperature is also going to increase. That means internal energy is also going to increase. Internal energy increases, that means delta Q is going to be positive. That means the system is going to accept heat. Going from B to C, B to C it's an isobaric process. Isobaric process है तो delta Q will be equals to NCP delta T. Now here also pressure is constant, volume will be directly proportional to temperature. Volume बढ़ रहा है तो temperature भी बढ़ेगा, तो NCP delta T will be equals to positive. My dear students, again Q positive, Q positive. From C to D, Q will be negative, Q will be negative. Just the vice versa reason for this. Alright students, so what is going to be the net QH? Let us just figure it out. From A to B, Q from A to B will be equals to CV, because it's an isochoric process, into delta T. So that is going to be nothing but TB minus TA. Students, observe here, N, what is this gas? Helium, monoatomic, 3R by 2 TB minus TA. This can be written as 3 by 2 nRTB minus nRTA. Alright. What is nRTB? 2 P naught into V naught. What is nRTA? P naught into V naught. Overall, this entire thing can be written as what? 3 divided by 2 P naught V naught minus P naught V naught. That means this will be equals to simply P naught V naught. Alright. So this heat is how much? 3 by 2 P naught V naught, my dear students. Very simple to understand out here. Okay. Chalo, let me rub this particular part and find out what is going to be the work done in the BC process. So, my dear students, not the work done, the heat. Now, in the BC process, my dear students, heat is NCP delta T. Alright. So, it is going to be NCP for a monoatomic is going to be 5R by 2 into delta T. Delta T, if I kind of solve it, that is same concept again. TC minus TB. TC minus TB. So this can be written as 5 divided by 2 nRTC minus nRTB. My dear students, nRTC is equals to what? 2 P naught V naught. 2 P naught into 2 V naught. That means 4 P naught V naught. So this can be written as equal to 5 divided by 2 into 4 P naught V naught. And this, if you observe, is going to be 2 P naught V naught. My dear students, if you calculate this, this will be 5 P naught V naught. So the heat in this process is 5 P naught V naught. Alright. इसको हम consider नहीं करने वाले because heat is going out. Heat is not coming into the cycle in this process. So efficiency is only the amount of work done by the heat extracted. Alright, fine my dear students. So given this particular thing, my work is done now. Alright. So we have a bigger one. Okay. So what should be the efficiency? Work done, P naught V naught divided by 3 by 2 plus 5 P naught V naught. Okay, so that's the efficiency out here. We will multiply this by 100 because it is asked in terms of percentage. P naught V naught will go to cancel. So this is going to be 3 by 2. 2 is going to come to the numerator. Alright, so this is going to be somewhere around 13 into 100, my dear students. This is going to give you approximately a value which is going to be equal to, this is going to be approximately equals to 0.154. So that is going to be somewhere around 15.4%, my dear students. So option A is going to be the correct answer out here. Alright, I hope everybody understood. Let me just summarize this very quickly. To find out the efficiency of any general cycle, my dear students, it is simply the work done in that particular cycle by the amount of heat extracted. This is what you need to remember. This is the important point out here. Now what is the work done? It's the area enclosed within the cycle. So which is very clear that it is P naught into V naught. Okay, that is very clear. P naught V naught is the work done. Heat is extracted in two of the parts, this and this. In this and this, there is no heat extracted. Alright, I told you the reason behind that, so you can just revise it by going to the video once again. So you calculated the heat in this processes. In this NCP delta T, in this NCP delta T. Alright, here the volume is constant. Okay, and here the pressure is constant. So that way you get the heat in the process, which is equals to 3 by 2 P naught V naught plus 5 P naught V naught. So we get this particular thing, and this gives me the net efficiency of the cycle. Alright students, let's go to the last part of the last section of this particular session out here of the second law of thermodynamics. And what do we see here? A lot of students have told me, sir, Carnot's engine एक बार करा दो sir, please. Alright, so with good visualization I have tried to bring in to you the different stages of the Carnot cycle. So we will just go ahead and look at that right now. Fine. So my dear students, this is what we have as our Carnot cycle or the Carnot's engine. Okay. There are 4 steps or 4 processes that goes on happening out here. The first one is called as your isothermal expansion. So this is the first part. Okay. Then what do we have? Let me just pause it at the right moment so that we have it out here. So it kind of goes there, and finally, yes, The last stage I'll draw. Okay, so in the first stage what happens is isothermal expansion. So it is basically on a hot this thing, it accepts heat. All right students, the first stage, it goes from this particular point to this particular point out here, from one point to the second point, from P1 V1 to P2 V2 out here. All right, so this first process out here is isothermal expansion. Temperature remains constant, it is constantly absorbing heat and it is expanding P1 V1 to P2 V2. Second thing is your adiabatic expansion. So no heat accepted, it just goes on expanding out here. Now let's say the temperature out here is T1, so it goes from here to here, after that from here to here, adiabatic expansion to this particular point here, and after that this is nothing but your isothermal compression, my dear students. All right, and finally it kind of goes, and this is your adiabatic compression, adiabatic compression. All right, so my dear students, these are the 4 stages of your Carnot cycle. All right, now same concept we are going to utilize out here. Now what is the efficiency? They say the efficiency of the Carnot cycle is the maximum. All right, so how do we actually get it? Let us go ahead and understand that particular aspect. So we'll kind of move ahead and we'll go to this. So in the first thing, that is the adiabatic, in the isothermal expansion, this is the amount of work done, change in internal energy is 0, amount of heat extracted is equals to nothing but W1. All right, this is the first step. All right, what happens in the second case? It is the adiabatic expansion. In the adiabatic expansion, heat extracted is 0, no heat, it is adiabatic in nature. Change in internal energy is NCV delta 2 minus delta 1. The work done will be negative of that, so this is minus NCV T2 minus T1. All right, in the third case we have got isothermal compression. All right, isothermal compression, this is the part that we have out here, which is equivalent to this. We can see here it's on the cold surface out here. Then this is my isothermal compression, so work done will be nRT2 because it is happening at temperature T2, ln V4 by V3. All right students, and finally we have got your adiabatic expansion. Q2 is equals to 0, change in internal energy is this, work done will be equals to this much. Very simple, you know all these formulas, you have already spent so much of time out here. Now my dear students, ultimately this is the chart that I want you to focus on. 4 stages: isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. These are the work done in the different processes. All right, in order to find out the efficiency of the cycle, my dear students, we need to find out what is the total work done and how much was the total amount of heat that was given to the cycle. All right, so the total amount of work done, if you calculate this plus this, is going to cancel out to 0. This and this comes out to this value out here. All right, and the heat that was actually extracted in the cycle was in the process 1. This heat, this and this, is ultimately equal to 0. There is no heat extracted because these are adiabatic processes. Okay, in this Q2 was actually liberated to the surrounding, so it was not extracted. Okay, only Q1 was extracted, so total amount of work done is equal to this, total amount of heat extracted is equal to this. Ultimately, if you have to find out what is the efficiency of the cycle, my dear students, and efficiency will be 1 minus T2 by T1. So this formula, that is this formula divided by this. You do it, you will get this as the answer. Very simple. Okay, let us look at a very interesting question on the concept of Carnot cycle. All right, and the efficiency process. Okay, chalo, let us go ahead, and this is my last problem for today, my dear students. What do we see here? A diatomic ideal gas. We have taken what? We have taken a diatomic ideal gas. So diatomic gives me gamma is equals to how much? 7 divided by 5. So this is the information that I extracted from this particular question. What do we see here? It's working substance, blah blah, everything. If during the adiabatic expansion part of the same, the volume of the gas increases from V to 32 V. Students, we clearly understand This is the part which is showing adiabatic expansion. What are they saying? From the in the process that goes from 2 to 3, this process here, volume here was V, here it became 32V. This was at a temperature T1, let's say this one is at a temperature T2. Students, can I compare, like, which one is going to be at a higher temperature and which one is going to be at a lower temperature? It's very simple to understand. Dekho, adiabatic expansion causes cooling. We have studied the tire bursting thing, adiabatic expansion. It causes cooling. So that means T2 is going to be lesser than my T1. T2 less than T1. Simple idea. Okay. They have asked us that in this adiabatic expansion process, the volume changed from V to 32V. Then find out what will be the efficiency of this cycle if the gas used inside this portion was a diatomic ideal gas. Alright students. Now what is the idea or how to do this kind of a question? Simple idea. We know efficiency is basically equals to 1 minus T2 by T1. That is the cold temperature by the hot temperature. Alright. Now if it is an adiabatic process, my dear students, then I know Tv to the power or T1 V1 to the power gamma minus 1 will be equal to T2 V2 to the power gamma minus 1, which kind of tells me that my T2 by T1 will be equals to V1 by V2 to the power gamma minus 1. Very simple idea. It's an adiabatic process. This one. So Tv to the power gamma minus 1 is going to be constant equation of the state for all adiabatic processes. Alright. What is V1, my dear students? V. What is V2? 32. Okay. So this is going to be 1 divided by 32 to the power. Gamma is 7 by 5 minus 1 is going to be 2 by 5. Students, 1 by the 5th root of 32 is going to be nothing but 2. And uska square, that means 1 by 4. Alright. So T2 by T1 will be equals to nothing but 1 divided by 4, that is 0.25, my dear students. Then efficiency of this will be equals to 1 minus 0.25. So that should be equals to 0.75. So option C is the correct answer. Alright students, that's it for today's session. I hope you have liked all the problems, the concept in this, the heat engine, the refrigerator. The heat engine, if it is working backwards as a refrigerator, then how to find out in general the efficiency of any given cycle, and finally looked at the efficiency of a Carnot engine, okay, which is generally the maximum. We kind of find it out from the derivation that we have seen here. Other than that, we have also looked at that efficiency of the engine. If it is maximum, then what is the condition? That is your QC by QH is equals to T2 by T1 or TC by TH. Alright. These are all the important concepts which is important for the numericals of the second law of thermodynamics, and that's it. Beyond this, there is nothing else, or the concepts consolidated, everything served as a package for you guys. Alright. So thank you guys for enjoying the entire series, and today was the last session on the entire of thermodynamics. If you have to revise, go back to the first session, watch the videos once again, go through it multiple times, enjoy it, like it, and share it as much as possible. Okay, God bless you all. Bye bye and take care.